Welcome to network lecture of our digital forensics course. Previously, we introduced data forensics, explained the tools, introduced file systems and explained them in detail. Also, we mentioned how to compile evidence. Now we would like to focus on reliably collecting evidence from networks. Then we will continue with the rest of the curriculum. In this lecture, we will define layered structure of computer networks, both OSI layers and TCP/IP layers. Then we would like to focus on different layers, second, third, fourth, and seventh layer, and how we number these layers. Then we would like to explain how to use captured network data as evidence. Also, we would like to mention encrypted communications and the metadata of computer networks. OSI stands for Open Systems Interconnection. It is designed for better interoperability in between computers. OSI defines 7 layers. These are theoretical layers. They exist, but they are not in use currently. But they build the foundations of modern computer communications, and how we do the numbering in the layers are based on this idea. The first layer of OSI is the physical layer. It defines physical properties of the communication medium. Either it could be a wire or a wireless medium or electromagnetic waves or anything else. You may think of even pigeons that carry a piece of paper from one place to another. It doesn't interfere with the second layer. The second layer communication is built to make connections in between two nearby devices. So now I can make one-to-one communications with one of my peers, but there is no network defined yet. If every device makes one-to-one connections in the parties that they are in their reach, then actually some kind of abstract network emerges. The third layer is defined on that idea. When you define the third layer, you actually try to explain how one device should send a message to another device, and that device may not be in the near vicinity of that first device, so the message should take hops, should be transmitted to one of the nearby nodes, and this node may transfer it to another node, and this transmission continues, and finally it finds the target node. To do that, in the second layer, in the third layer, you need to have some kind of routing protocol, and you need to define addresses. IP addresses are the addresses that I'm mentioning, and routing tables are the routing information that we obviously use in the internet. In OSI, these are more abstract, but in the TCP/IP layers, these are realistic. The fourth layer is managing transportation of messages from one end device to another end device that may be anywhere within the network. So you can start your communication from a computer in United States, and it may end up somewhere in Japan. During this communication, the packages could be transmitted to first England, then somewhere in Europe, then to Turkey, maybe to Russia, and then Japan. You don't know. But all these communications are managed end-to-end in the fourth layer. So let's try to summarize this one more time. The second layer communication actually gives us communication capability with the devices that are closer to ourselves. The third layer builds a network by connecting all these peerly connected devices, and as all of these devices are interconnected, the idea of network materializes from that. This network has some routing information in it and also has addresses for each endpoint. And when you have the endpoints, if you want to send one data from one side to another side, you manage this in the fourth layer. So you manage the length, the speed, and all other stuff in the fourth layer. And probably you know this is the most common protocol we are using in the fourth layer is TCP. There is also a fifth and sixth layer. We will hardly mention them. The fifth layer is designed to build a session in between these two parties. Imagine you have two different computers in two different locations and they have transporting messages. So they are communicating already on the fourth layer. In the fifth layer, you need to define sessions, because in one session you may use messages for transferring sound, and in the second one you may use a session to manage transferring video. So actually you may require two different sessions, or you may send an email and at the same time send a file to the same computer, so you need to manage two sessions. In the sixth layer, you have the presentation layer. The presentation layer is actually designed to semantically understand the messages that are sent back and forth. So when you send an email or when you send a video, it should be understood at the sixth layer. So the receiving computer should say, okay, this should be a video file, or this should be an email, or this should be a text message, anything else. And after this kind of presentation data is added to the original message, it should be handled to the seventh layer. Seventh layer is the application layer. The application layer is responsible to interact with the user. So whenever you receive an email, you will visualize it. Whenever you receive a voice message, voicemail, the application should interpret it and play it through your headset. And this is the responsibility of the seventh layer. Why we have some kind of interesting pattern emerging in this slide? The reason lies in the TCP/IP layers. Actually, TCP is the fourth and IP is the third layer, and this is the very basic structure of current internet. TCP/IP layers is not built on OSI layers, and they are not in line actually. As a result, the fifth and sixth layer actually doesn't exist in TCP/IP layers, and they are all merged in the application layer as the seventh layer. So in practice, we don't have fifth and sixth, but we let all the responsibility of this to the seventh layer, to the application layer. We have a second layer communication in TCP/IP layers. Maybe not exactly as designed in the OSI, but still we have it. And we have some channel control on that, so we can make devices communicate with each other in the near vicinity. This may be thought as Ethernet devices or Wi-Fi devices, or maybe 3G or GPRS devices. These are the basic examples of second layer communication. So if you think of all these details, you have device-to-device communication in the second layer, you have the network in the third layer, you have the transportation in the fourth layer, and you have the applications in the seventh layer. What you should take care of when you are trying to capture network data as evidence. What you can collect from the second layer is the devices and the device addresses that are in the close vicinity. If you have access to an Ethernet network, whenever you tap this, you learn about the physical addresses of the network devices that are in use, and also maybe the mapping in between the physical addresses, physical locations, and the IP addresses. This is what you can learn from the second layer. Also, it is very hard to reason about the correctness of this second layer communication. The reason is, in the close vicinity, the network designers think that the environment is secure enough, so they don't actually take cryptographic actions that much. Most of the time, if you just join the network in the second layer, you are free to see the structure, but you don't have any mechanism to prove that it is correct or not. When you try to check the communication in the third layer, you see the receiving and sending IP addresses that are traveled across your network. For example, if you have the whole management of the, let's say, of the network in Turkey, and someone is sending data from Europe to China over Turkey, then you can be able to see the contents of the data on this network, because actually the whole internet is something like sending buckets of water to during just like firefighters. Every message is passed from one computer to another nearby computer, and at the end a whole chain emerges and you send data from one end of the world to the other end of the world. This part of information may or may not be secure. There is a communication protocol called IPsec that you can use in the third layer to encrypt and secure the communications, so eavesdroppers cannot see the contents of the messages or the source or target addresses of the messages based on the configuration. However, normally, if you don't use such encryption mechanisms, anyone could say that it has one of the IP addresses, so anyone on the network could receive the sent the sent IP address, reroute the traffic, or may generate fake messages from one side to another. So when you collect information about this layer, it is very difficult to understand that if they are the original files or not. This is called IP spoofing, so you can actually make changes, modify the message on the fly. You can make changes on the source address, you can make changes on the target address, and also you can reroute traffic from one direction to another direction. And this may be problematic to prove the correctness of evidence. In the case of IPsec, we will mention that later whenever I mention the encrypted communications and metadata. For the fourth layer, we mostly try to manage the speed and some endpoint relevant data, and also the fairness of networks for many parties to use the same network infrastructure. This is done by TCP. And for TCP communications, actually these TCP communications end up in the endpoints. So if you are not one of the endpoints, you may still see the contents of the messages, but actually you cannot prove that they are coming from the same source or they are directed to the same destination address. The encryption mechanism built on the fourth layer is mostly TLS, or with the old name, also known as SSL, Secure Sockets Layer, or Transport Layer Security. If you have TLS, you cannot see the contents of the message, but you cannot see the contents of the message on the fourth layer. You can still see the IP address of the source and target parties. For seventh layer communication, actually you are in the application level now. So you are interacting with the user, and the user may or may not use encryption. For example, SSH protocol is a nice example of application level security protocol. If everything is hidden with SSH, you can still see the structure of TCP packages, but you cannot read the contents. You can still read the network addresses, target network address or source network address, but still you cannot see the contents of the seventh layer protocol. If everything is open, by open I mean everything is in plain text, not encrypted, then you can modify all these network messages. You can read them and you can also modify them. And this is the case that you need to be careful about collecting evidence, because it is very difficult to prove the integrity, the non-modified nature of the collected network data. This both things, the encryption and integrity of the evidence, seems counterproductive. The reason is actually the idea of secure communications. If you want to build integrity and security in communications, most of the time you encrypt it and you also prove that it is not modified on the way. But if you are just wiretapping, eavesdropping, and collecting data from the network, then actually you are not sure that anything is actually proved to be non-modified, and therefore you need to have a witness, or you need to have a network log, or the internet service provider should also try to ensure that these two parties are actually communicating. Otherwise, all information that you collect from the network should not be useful as evidence. One of the things about these captured network data, or how we can use this, let's say, plain text network data as evidence, you need to have complete control of the networks that generate these sent and received messages. So your best shot is to have some collaboration with the internet service provider, and internet service providers may ensure that the parties actually have the specified IP addresses, they are actually using the same physical addresses during the communication, and they are passing from one location to other location, and the routing tables are not modified during this time. Most of the time, that's the reason that legal authorities collaborate with the internet service providers, and they try to fetch information. Otherwise, the collected network data is probably just a bunch of garbage and cannot be used as reliable evidence. I would like to make one final note about encrypted communications and the metadata. Imagine the case with IPsec I mentioned for third layer communication. IPsec has two modes. You can hide the source and target addresses or not. Imagine that you didn't configure IPsec protocol to hide the source and target addresses. Then the contents are unreadable for an eavesdropper. So the eavesdropper cannot understand if the fourth layer protocol is TCP or UDP, or if they are making communication between one party or another. But still, the eavesdropper can reason that one IP address, let's say 1111, is communicating with another IP address, let's say 2222. And it is the same for fourth layer communication. Even if you use TLS in your communications, you can hide the contents of the messages that you exchange in between a server and a client. But still, you know the address and port of the client, and you know the address and port of the server. So you can still ensure that this guy with this IP address communicate with the service of that server. Let's say it is communicating to email services of one email provider, let's say Gmail or Hotmail, and you can ensure that there is some kind of communication happening in between, even though you cannot read the contents. That's all for this lecture. Goodbye and see you in our next course.